Thank you, Andrew. And so the title of my talk is Theoretical and Experimental Investigation of Fibre Nonlinear Effects in Ultra-Wideband Optical Transmission. And this work obviously has been a big collaborative effort between both the groups at UCL and the TASM. So we're part of the UNLOCK program. We're investigating how does the throughput of an optical fibre system increase as we increase the bandwidth. So as we go from the conventional C-band transmission to C plus L band, S to C plus L, increasing the bandwidth from the 35 nanometers that is available within the C-band to 100 or up to 400 nanometers, which is the bandwidth of the low-loss window of silicon fibre. So, looking at the equation for the capacity of a system, this is the well-known Shannon capacity formula for a linear system. There's two ways in which we can increase the throughput. The first is to increase the signal-to-noise ratio and make use of that increased signal-to-noise ratio to send more bits per symbol. And this is actually within the log, so there's a limit to the extent to which we can push this. But the second method to increase the throughput is to increase the bandwidth. And in a linear system, the bandwidth increases linearly, the capacity increases linearly with the bandwidth. So outside the log, we can get potentially very big increases in the capacity. However, in a nonlinear system, it's not necessarily true that increasing the bandwidth of the signal will lead to a linear increase in the capacity. Because of the effect of nonlinear interference, so the power in the other WDM channels, other frequencies within the WDM signal, will cause distortion, cause noise-like effects on the channel of interest. So we've been working on how to, what the impacts of these nonlinear effects are when we increase the bandwidth of the signals to very large values, much larger than the 35 nanometers of C-band. So let's just have a look at what the nonlinear effects that we're considering are. First of all, there's the effect of the current nonlinearity, the four-way mixing, which has been discussed by previous speakers. So we get four-way mixing occurring, and we get nonlinear interference between the products generated by the four-way mixing. And we have some quite accurate, quite useful models to estimate the effects of four-way mixing. In particular, we've been looking at the Gaussian noise model developed by Puncellini and colleagues at the Polytechnic of Turin. And the second effect, as you get to very large bandwidths, is stimulated Raman scattering. And with SRS, we observe a transfer of power from the high-frequency channels to the low-frequency channels. And it's thought that this will actually be the ultimate effect which limits the degree to which we can increase the capacity is through increasing the bandwidth of the signal. So I'll talk a little bit about a couple of experiments and theoretical studies that we've done looking at both these effects. So first of all, we carried out experiments looking at extending the bandwidth of the signal to up to 7.3 terahertz, and just investigating the effects of four-way mixing and comparing the experimental results with the results that we obtained with the analytical models. And then following this, we've extended the bandwidths of our studies up to 20 terahertz and incorporated the effects of stimulated Raman scattering into our models to try and estimate what the effect of this effect will be on the throughput. So this is a very simple equation that we can use to incorporate the effects of nonlinearity into the performance of the system. We can express the signal-to-noise ratio using this formula here, where we have the conventional amplifier spontaneous emission noise here, where n is the number of amplifiers, PASE is the power, noise power added by each of the amplifiers. We then have this nonlinear term, which this is a noise-like term caused by the four-way mixing, which increases or proportion to the cube of the signal power. And this factor here, eta, we have formulas based on the dispersion of fibre, nonlinear coefficient, and the power profile. That means we can very rapidly calculate what this value of eta is. And then finally, in any practical system, we have the signal-to-noise ratio penalty just due to the practical transceiver implementation. So we use D2A converters, A to D converters. They have quantization noise. We also have electrical noise in modulated driver amplifiers. And these can be combined or can be added into the SNR equation using a term that's shown here. So as I mentioned, this nonlinear interference coefficient eta can be calculated analytically very rapidly compared to the very time-consuming split-step Fourier simulations that have to be performed if we don't use these analytical techniques. But it has been questioned, we've discussed with colleagues, and it's been questioned whether these analytical models are accurate up to very large bandwidths. It's been confirmed that they're accurate for C-band transmission, but what's about when we increase the bandwidth beyond C-band? So this is the aim of the experiments that we performed. We increased the bandwidth of the signals up to 7.3 terahertz, so that's C plus L band, and we can check the accuracy of the Gaussian noise model with our experiments. So this is the experimental setup that we used, the recirculating loop testbed in the optical networks group lab at UCL. I'll just go through the experimental details. So we start with a super-channel transmitter, which has 7 subchannels. Each of those subchannels operates near 40 gigabaud and modulated using D2A converters with 64 QAM signals. We use 2 modulators to ensure that we have decorrelated odd and even channels, so we don't get any correlation effects which can affect the result. We carry out polarization multiplexing, so we can transmit dual polarization signals. This is a technique that has been developed, the work on this is led by Daniel Ellison at UCL, and also the group at Aston has also been developing this as well. This is a method to emulate a large bandwidth signal using amplified spontaneous emission noise. It avoids the need for hundreds of lasers, which basically costs a lot and takes up a lot of space in our experiments. Instead of using many transmitters, we can emulate the effects of these other channels just using amplified spontaneous emission ASC noise. So we have C-band and L-band ASC noise. We shape them using these wave shapers or wavelength selective switches, and then we couple those with the channel of interest. I should mention that these experiments have been led by Gabriele Sbarger and Ligia Calvino, together with our colleagues at Aston. This just shows the spectrum of the signal. We have quite flat path spectral density in the C and L bands. The signal is then launched into our recirculating loop, so we use 100 kilometers of high fibre. Here we separate the L and C bands into separate amplification. Then at the receiver, we're using 63 gigahertz bandwidth coherent receiver, which can detect all 7 subchannels. And it's important when we're measuring the signal-to-noise ratio to be able to isolate the SNR penalty due to the transceiver from the SNR penalty due to nonlinear effects and nonlinear ASC noise. So we quantify the signal-to-noise ratio of our transceiver. With a single 40 gigabaud signal, we have an SNR of just over 20 dBs. Due to crosstalk from the other channels, this drops to around just under 19 dBs. These are the measurements of the transceiver signal-to-noise ratio when we add the signal together with the specially shaped ASC noise, which is being used to emulate the other WDM channels. And then we characterize the performance, and we checked the performance against the theoretical predictions using the Gaussian noise model. So let's start with the results from the Gaussian noise model. So these are the simple formula that we use to calculate that factor eta and put it into our signal-to-noise ratio equation to predict what the SNR will be. This is for a number of 4 different signal bandwidths, going from narrow bandwidth, just a single channel of 40 gigahertz bandwidth, up to a large C plus L band 7.3 terahertz bandwidth signal. And you can see that in each case we have this optimum launch power per channel, and also as the bandwidth is increased, we expect due to four-way mixing, due to nonlinearity, a drop in the signal-to-noise ratio, which will result in a drop in the achievable throughput. So how do these model predictions by the model compare with the experiments? So the markers on the plot here to show what the experimental measurements were. And you can see that there's very good agreement. So that prediction by the Gaussian noise model is quite accurately predicting what we actually observed in the recirculating loop experiment. So you can see that as the bandwidth has increased, the penalty becomes larger, but there's a logarithmic dependency on the bandwidth. So the signal-to-noise ratio drops, but it doesn't keep dropping linearly. There's a logarithmic reduction in the drop in the signal-to-noise ratio. So what does this mean on the throughput of the fibre? So the throughput is really the quantity of interest, not the signal-to-noise ratio, but how many terabits per second can we transmit. And so we use mutual information, which Eric introduced in the last talk, as a performance metric. So the mutual information represents the largest achievable information rates for the system for a given modulating format. And this just shows the mutual information, the number of bits per symbol that we can transmit as a function of the transmission distance for two different bandwidths, for the 40 gigahertz to 40 gigabaud single channel signal, and for that very wideband 7.3 terahertz WDM signal. So you can see that there is a penalty, there's nonlinear penalty of around 1.5 dB. But it's not a huge penalty, 4.5 bits per symbol, but it's not a huge penalty. It's relatively small, considering the vast increase in the bandwidth and the amount of data being sent. So achievable rates are reduced due to nonlinear interference by about 15% at 2,500 kilometers. But we get 150 times increase in the throughput due to this bandwidth increase. So our experiments are showing about 46 terabit per second transmission with relatively small loss in the mutual information and the number of bits per symbol due to the Bohr mixing, due to the nonlinear curve effect. So that's the experimental assessment of the 7.3 terahertz bandwidth signal. We'll now move on to our studies, and this is work that's being done primarily by Daniel Zemrau at UCL, looking at the effect of stimulated Raman scattering as we increase the bandwidth up to 10 or 20 terahertz. So the effect of stimulated Raman scattering is to transfer power from the high frequency parts of the signal to the low frequency parts of the signal. And this just shows a spectrum of the Raman gain coefficients. We get maximum gain when the pump and the Stokes wave are separated by around 13 terahertz. And we can approximate this gain spectrum just with this linear shape, with this triangular shape. And Daniel's done some very nice work deriving a closed form analytical formula that allows us to use that approximation to estimate the impact of SRS on the throughput. So the effects of stimulated Raman scattering can be seen in this calculation, showing the lowest frequency channel power profile and the highest frequency channel profile, power profile along each amplifier span. You can see that there's quite a significant difference in the signal power at the end of each span, around 5 dB difference. Now this can be equalized. We can use adaptive gain equalizers, which can equalize the launch power again at the next span. But this will lead to a difference in the optical signal-to-noise ratio across the WDM signal. So the first step in dealing with stimulated Raman scattering is to use gain equalization. We've derived a closed-form expression to calculate the frequency-dependent OSNR, including the effects of stimulated Raman scattering and Fourier mixing, in which we've, as I said, approximated the Raman gain spectrum with this linear function. The details of this model can be found in this Optics Express paper, which I think is now available. And I'll describe a few simulations that we performed on a typical link to investigate the impact of SRS. So the link that we considered in this study is based on standard single-mode fibre. It has a 3,000 kilometre length. We're assuming lumped amplification with a 5 dB noise figure. keeping 100 kilometer amplifier spans. For this particular plot, we're looking at 10 terahertz signal bandwidth, and the OSNR measured with 10 gigahertz resolution. So first of all, calculating the optical signal-to-noise ratio, including the effects of four-way mixing, just using the Gaussian noise model, you get this quite uniform OSNR across the spectrum. But when we include the effects of SRS, we can see this very pronounced tilt in the OSNR. So we have quite high, actually increases in the OSNR at the lower frequencies, quite a big drop in the OSNR at the high frequencies. What we can do is use adaptive modulation, which means that for the channels that have a higher OSNR, we can transmit more bits per symbol by using coding and higher order modulation formats. And we can, for the channels that are experiencing a drop in the OSNR, we can go to lower mutual information, so we can go to lower number of bits per symbol. So the two approaches that I think will deal with SRS are the adaptive equalization, gain equalization, to take into account the power tilt due to SRS. And then secondly, to use non-uniform spectral frequency signal formats across the spectrum. So here's some calculations of the achievable information rate as we increase the signal bandwidth up to 20 terahertz. If we neglect the effects of stimulated Raman scattering, you can see the predictions for this particular 3,000 kilometer link are just under 150 terabits per second. Assuming we're using uniform spectral efficiency, so we're not using this adaptive modulation format, but we're keeping the modulation format uniform across the spectrum, we can see quite a considerable drop in the achievable information rate from 140 terabits per second down to less than 100 terabits per second. And this is with the optimized launch power. We've also derived equations to give us the optimum launch power using this analytical expression that Daniel has derived. This gives us quite similar results, maybe slightly lower achievable information rate. One approach to try and deal with SRS that's been proposed in the literature is just to keep the launch power low, keep the signal power low, and just try and avoid stimulated Raman scattering altogether. If we do that, we actually experience further drop in the achievable information rate. So this isn't the best strategy to deal with SRS. We don't want to just try and avoid it by using low signal power. How about if we then go to adaptive modulation formats? So we deal with SRS using different modulation formats at different frequencies. And we recover a lot of this drop in the throughput. So in this case, we have an achievable information rate of over 120 terabits per second at a bandwidth of 20 terahertz. So I'll conclude first of all by just summarising the results of the GN model, looking at four-way mixing. We've confirmed in our experiments that the GN model is quite accurate, even up to quite large bandwidths, up to 7.3 terahertz. We've experimentally confirmed the predictions of the Gaussian noise model with the nonlinear interference noise power grows approximately logarithmically with the bandwidth. And we've shown that it's by far the benefits of increasing the bandwidth outweigh the nonlinear growth. I think you have to go to quite large bandwidths before we start to see the nonlinearity actually cause reductions in the throughput with increasing bandwidth. We've also looked at the impact of stimulated Raman scattering. The signals bandwidths up to 20 terahertz, and we've shown that with adaptive gain equalization and adaptive modulation formats and coding, we should be able to minimize the impact of Raman scattering and avoid too big a drop in the throughput. We're predicting throughputs of about 120 terabits per second over 3,000 kilometers of standard SMF with 100 kilometer amplifier bands in the case of 20 terahertz signal bandwidth. Okay, so that concludes my talk. Thank you for your attention.